It's my pleasure to present our work on multiple label image recognition using a novel approach called GKGNet. Multiple label image recognition is a challenging task that involves assigning multiple labels or categories to an image. For multiple label classification, the key is to accurately locate the regions of interest within the same image in order to identify different categories. CNN and vision transformers are two popular approaches. However, they may not be able to detect discontinuous objects or may be affected by background noise, making them suboptimal for multi-label classification. Our model, GKGNet, accurately captures the relationships between patches and labels. Using a unified graph representation that can focus on discontinuous objects while excluding the background noise. Both patches and labels are represented using graph structures. Additionally, we have established two types of graphs. Patch-level graph is used to extract visual features from patches. Cross-level graph is used to establish correlations between target labels and related regions of interest. In our model, we can observe that the label nodes accurately selected the target regions through graph connections. KNN is commonly used to construct a graph, where each node interacts with k nearest neighbors. However, this may not be the optimal way to build the graph. The first issue is that a fixed value of k is not able to effectively handle objects with different scales. A large value of k is not favorable for small objects, while a small value of k is not favorable for large objects. Another issue is that KNN limits the ability to obtain co-occurring information from high-level labels for individual labels. To address the limitations of traditional KNN, we propose the group KNN for graph construction. Traditional KNN is limited to selecting a fixed number of neighbors. Group KNN splits each node into G groups. Each sub-destination node selects to connect with sub-source nodes within the same group. When the neighbors of distinct groups overlap, the number of selected source nodes decreases. Hence, our group KNN can achieve dynamic connections of variable quantity. In the visualization, it can be observed that group KNN effectively adapts to the size of objects. For smaller objects, the final selection of the label node is effectively concentrated around the region containing the target object. For larger objects, the final label node selected a sufficient region and attended to different parts of the object. Moreover, by utilizing different subgroups, Group KNN extracts co-occurrence relationships in a flexible manner, such as between remote controls and televisions, or cars and traffic lights. GKGNet captures the spatial relationship between patches and the label patch correlation by applying patch-level and cross-level group KGCN as mentioned before. 4 stages of networks are used to capture multi-scale features for robust prediction. The classifier utilizes both patch nodes and label nodes output by the last stage for multi-label classification, and we utilized a composite loss function for training purposes. Our experiments demonstrate that GKGNet achieves state-of-the-art performance on the MSCOCO and VOC 2007 datasets, with significantly lower computational costs. We reported and compared the per-category recognition accuracy on the MS-COCO dataset, and observed that our model achieved the best performance for 76 out of 80 categories. We conducted ablation studies to assess the impact of various model components, object scales, the number of groups G, and the number of neighbors K, which confirmed the effectiveness of our network, particularly in improving performance for smaller objects. Furthermore, Group KNN exhibits potential in general image recognition. Applying Group KNN to the pyramid VIG tiny yields significant performance gains, providing strong evidence for the superiority of Group KNN-based graph construction. Thank you for listening.